Cool. Okay. Today, we need to finish up chapter 3. And that should put us in line for a review next Friday on the first 3 chapters and an exam the following Friday. Okay. Just going to get the lights on and see what happens. Let's glare up. Like that. Okay. So now we're going to look at atomic structure. And the periodic table is, at least now, after decades of refinement, periodic table is arranged in such a way as to, actually it demonstrates atomic structure. And you'll see why pretty soon, I hope. First, we want to look at the internal structure of the atom. Of course, the name atom means that it can't be reduced any further, right? And then in one sense that's true, because if you break an atom apart into its elementary particles, then it doesn't have the characteristics of the element. But it does have parts. And central to the atom is the nucleus. Right? It's a very dense, very tiny part of the atom. And it has at least a proton. And that's the case for hydrogen. But anything above hydrogen and some forms of hydrogen also have neutrons. They're basically the same mass, similar masses. Neutrons just a tiny bit heavier. And then this constitutes the positive dense center of the nucleus of the atom. And then out here somewhere are your electrons. They have equal size, magnitude charge, but opposite sign to the protons. So in a neutral atom, you'll have exactly the same number of protons as electrons. That balances the charge. Okay, so there's our electron, we covered that, protons, neutrons. Okay. Now this just gives you an idea of the relative mass of each of the particles. So here the neutron and the protons are almost identical in mass. 10 to the minus 24th grams, which is still pretty small. But if you compare the magnitude here, 10 to the minus 24th, to electron, 10 to the minus 28, you find that the protons and neutrons are 4 orders of magnitude heavier than the electron. And these are relative numbers. If the electron's 1, protons 1800. So I mentioned the characteristics of the atom with the dense nucleus, and that's where the protons and neutrons reside. And because you have the same number of protons, same number of electrons, the atom is going to be neutral. Now, if you strip away 1 or more electrons, or you add 1 or more electrons, you shift that balance. Right? So if you add electrons, you're going to make your atom into a negative charged ion. It could be 1, 2, 3, 4, whatever. If you take electrons away, that's going to shift the balance toward the protons, which makes it more positive. And that's how you get ions. You only tinker with the electrons. If you mess with the protons, you might get a different charge, but you'll get a different element too. The number of protons determines the element. We'll talk about that in a minute. Yeah, question?
How do you
Add electrons? You could do it physically, you could do it in a chemical reaction. Okay? If you have a generator, a Van de Graaff generator, you pump out lots of electrons, and you can make ions pretty quick. But we're gonna focus on making ions with chemical reactions. So you transfer electrons from one place to another. And when you do that, you leave an excess of protons behind, and you overwhelm the protons in the destination. So you make that one negative, you leave more protons behind, makes that one positive. And that's one of the bases of chemical reactions, is you form ions and then you get electrostatic attraction. Okay. For example, try that again. For example, if you have sodium and chlorine, sodium is going, we look on our chart, see sodium is going to have 11 protons. That's the atomic number. And chlorine is going to have 17. That means they have 11 electrons, 17 electrons. But metals like to give up their electrons. Non-metals like to accept electrons, as a general rule. So if we remove one electron, send it over here, that means you've got only 10 electrons left. That means you have an excess of one positive charge. And if you bring that electron over here, now instead of 17, you have 18 electrons. And that gives you an excess of 1. Okay. Now that you have that difference of charge, they attract one another and you have table salt. We're actually talking about types of bonding here. So we're getting ahead of ourselves. Okay, subatomic particles, protons, neutrons, electrons. When we write a symbol for an element, and I'll use X as a generic because there's nothing up there on the board that's just X. There's an XE, there's no X, so I can use this one as a generic. There are 4 positions around the symbol that are reserved for information. Okay, we looked at one just a minute ago. This is for charge. You always put the charge up here to the upper right-hand corner. And if you have more than one of them, then you'll put a number down here, the number of atoms. Okay. On this side, designated by Z, that's the atomic number, the number of protons. Right, is Z. And that defines the element. The number of protons tells you that you have an element. So if you know that it has 12 protons, right, just look up there for 12 and you find that it's magnesium. So you can't have one without the other. And up here, you have the mass number. The mass number is equal to the number of protons plus the number of neutrons. Okay? So, if you have this number and that number, you can find out how many neutrons. You just subtract this one from that one. The number of neutrons equals A minus Z. Okay? So our chemical symbols, well, let's see, that's animation. Okay, for sodium, we had, I only showed you the 11, but this particular brand of sodium has a mass number of 23, so that means it has 12 neutrons. Okay? Okay. So when we name an element, and if we are saying that an element is all you have in this lump of something, you have a pure substance. There's nothing else in there to mix in with it. and it cannot be broken down into simpler substances by physical means. Right? An element can't even be broken down by chemical means. So that's as simple as you can get. If you have a compound, a combination of more than one elements, like our sodium chloride, then you can break it down into its individual elements by chemical means. Okay, and in this pure substance of an element, all atoms have the same atomic number. Right? And they possess the same chemical properties. Now let's think about the structure of an atom. From what we know at this point, we have our nucleus with our protons and the neutrons, and then we have electrons out here somewhere. We haven't defined how they're placed. But when you consider two different elements approaching one another, what do they see first? Electrons. So the structure of the atom out here with the electrons determines how an element will react with another element. Right? Now we know that they're linked, of course, but for chemical purposes, when they come together and react, that's the star of the show, the electrons. Okay? So the atomic number of an atom is number of protons and the number of electrons in a neutral atom. But we focus on the number of protons. And then if we know it's neutral, that means the same number of electrons. If we know it's charged, then we can also calculate the number of electrons depending on the charge balance, whether it's positive or negative. Now, I mentioned earlier that if we know the atomic number, we know the element, we know the number of protons. But not every atom in that mixture of pure element is the same. There are some of them that have a different number of neutrons. Now that sodium that we looked at earlier, right, it has 12 neutrons because of this difference. But there are other forms of sodium that might have different numbers of neutrons. We call those isotopes. Now, isotopes are different, but they're not chemically different. They behave the same way in a chemical reaction. And that's fortunate in some respects, because we don't have to worry about the isotope ratio in a given collection of an element when we do a chemical reaction. We can treat them all the same. So they have identical chemical properties. Their physical properties differ very slightly, and that's simply due to the difference in mass. Right? I think there's one isotope of sodium that's maybe 22 with 11. So that means it has 11 neutrons. These two will be different in their physical properties, right? And you can use those physical properties to separate them, okay? In what we call a spectrograph. A mass spectrograph will separate atoms of an element into their component isotopes. Okay. I'm not going to go into details of how it works, but it's based upon the difference in mass. Okay. But in a chemical reaction, I'll say again, they behave exactly the same. Most elements that you find in nature are a mixture of different isotopes. And for most of those elements, there is a major isotope, the most common one. And then there are just a few of different isotopes. Now, there are a couple of exceptions. Chlorine is one of them. 2 isotopes of chlorine, they're almost equally, same number. But most of them, you have a major, like carbon 12 is major for carbon, then you have carbon 13 is a little bit, an even smaller amount is carbon 14, which is the radioactive one that we use for carbon dating. Here's an example, silicon. So we have 14 protons in each one. That guarantees that it's silicon. And then the mass numbers are different because the number of neutrons are different. So if we have, let's see if we can do some detective work. Let's say our isotope has 23 protons and 28 neutrons. Okay, what's the mass number? 51, right? Add them together. Protons, neutrons makes the mass number. Okay, so that should come up. Here we go. Now, how do we identify the element? Simple. Yeah, 23. What's 23? You know what V is? Have you started memorizing your element symbols? You should. You should make yourself some flashcards. Memorize those that I gave you in that table, the periodic table that was outlined with the red and the pink background. Just those. You don't have to do the whole table. Just memorize those. And V turns out to be vanadium. Okay? Now, interestingly enough, while this defines the element, sometimes if you only know that one or something close to it, you can get pretty close to defining which one is which, because the masses of the elements also vary. As this increases, masses also increase. So if we only knew 51, let's see if we can get close to that. So if you look at the periodic table, you notice that these mass numbers up here get bigger. Now, they're not whole numbers, and I'll explain that a little later. But if you just follow along, say, okay, there's 50.9, 51.9, so that's closer to 52, and this is 51. So it's probably vanadium, even if we didn't know the atomic number. You can get pretty close. There are some where the masses are so close together that it's not definitive. But those are rare. Most of them, if you know the mass number or the atomic mass, which is different, and I'll explain that in a minute, then you can find out what the element is. Okay, so now for the difference between mass number versus atomic mass. We probably ought to say here, average atomic mass. What we're trying to do is present a value that is representative of the entire mixture. Right? And like we said, there are 2 or more isotopes usually in a natural occurrence of an element. Right? So they're not going to, the mass is not going to be exactly 12, and it's not going to be exactly 13, it's not going to be exactly 14. It'll be a weighted average, right? It's going to be close to this one because most of them are that. But you're going to have a little bit of this that skews it to the heavy side, and this even less skewed to the heavy side. So think of it as calculating your GPA, right? The course that has 3 hours weights the grade heavier than the course that only has 1 hour. It's a weighted average. So when we calculate atomic mass, what we're doing is we're taking a weighted average. So for 12, it's going to contribute 0.9889 fraction of the whole. Now, why did I say 0.9889? Because percent is a dimensionless number. And we want to know the fraction that's part of the whole. So the fraction is 0.9889. This fraction would be 0.0111. And this fraction, you can ignore it. It's too small. So to do the calculation, we really only need these two. All right, so if we were to take 12 and weight it by this value, that would give us the contribution of C12. Okay, and then we would weight it by C13 to this amount. Okay, so the total is going to be how much does this contribute plus how much does this contribute. So we can just pull out our calculator, do a quick calculation. 9889 times 12, and that's 11.867. Okay, and this one is 0.0111 times 13, and this one is 0.144. We add them together, and we get rounded off 12.01. Well, you can take it out too. Okay, so this is the atomic mass. Now, what values? See, we didn't put any values on that. I mean, first we said that this is the number of protons and neutrons, right? But that doesn't put a value. I mean, a dimension, a unit of measure with that number. Right? So we devised a unit of measure, the atomic mass unit, which is roughly equal to the mass of one proton. Not exactly, but for argument's sake, it's close enough. So we would say the average mass of a carbon atom is 12.011. Now, you're not going to find one that's exactly that because this is a weighted average, right? It's a collection. This will also mean something else later. I'll show you. But for now, it's that value, atomic mass units. Okay, so there was our calculation. And if we take, let me get my bearings, I don't want to run out of time. Okay, we're good. Say an element consists of 62.6% of one isotope with a mass of this, and it also consists of 37.4% of an isotope with this mass. Now, we just did a calculation where we said the mass is a whole number, like 12 and 13. Now, why are we starting off with a fraction? Well, we need an anchor point. In other words, we need to assume that something is an exact value, and then everything else is based on that. So the exact value for purposes of calculating atomic mass is carbon 12. Carbon 12 is defined as 12, just keep going, atomic mass units. That's defined. Everything else is compared to that. So because of that fact, everybody else, even if it's just one of the isotopes, is going to be a fractional value. Okay. We're not trying to confuse you here. It's just, that's just the way the ball bounces. Okay, so if we have, how would we calculate the average atomic mass for this element? Right? We have 186.956 times the fraction that belongs to that one, 626, right? And the other one is 184. It's a little bit lighter. So what does that mean? Probably has fewer neutrons, right? And its contribution is only 37.4%. Okay, so we can do a calculation. We just say this one has more weight, more contribution than that one by 0.626, 186.56. So that's 117.034. 17.034 atomic mass units from that isotope. And this isotope, 3740. Oops. Oops, something went wrong. Try that one again. Okay, this one gives us 69.172. Just add them together. One 186.2. 206. Oh, that's okay. So that's our rounding error. Okay. Now, how do we find out what element it is? Because we're not told how many protons. Remember, we can look for the mass. So you go to your periodic table and say 186.2. What's close to that? Now let's see. It's going to be heavier than the other one we looked at. 183, 186.207. RE. I don't think you had to memorize that one. So that one is rhenium. Okay. All right. Atoms of an element that contain a different number of neutrons are known as that ought to be fresh in your mind. Isotopes, yeah. It's not a trick question. Okay. Now we're going to look at periodic table. And historically speaking, scientists were beginning to realize that some elements had similar properties, physical and chemical properties, and they started grouping them together. First, they started off with the concept of triads, because they didn't know all of the elements at that time anyway. So the ones that they did have tended to group into groups of threes. And these three elements would have similar properties. They weren't exact, they were very close, and significantly different than their neighbors, any of the others that looked at. So those, we got the triads there. Then along came a German and then a Russian, who by that time they'd accumulated more elements and they started grouping them together. Actually, they were grouped this way. And these had similar properties, more elements together. And they noticed also a cycle, so to speak, of weights. In other words, you would have this group, and you put the groups side by side, and then you'd say, this one, the next heaviest one is here, but it has different properties. But it has members of its group. Right? And then the next heaviest one, and members of its group, and then you keep going, and then you get to the point where, well, if you go to the next mass that's available, you've actually got something that's more like this one over here. Right? And that's called a period, where you go to the end and you have to go back and start over again. Okay. Anybody had physics in here? Physical science? Heard about periodic motion? Think pendulum. A periodic motion is something that's moving, but it goes through a cycle and ends up back where it started. So that's what we're doing with the periodic table. The periods are the horizontal rows. So you go left to right, say you start at potassium, calcium, scandium, titanium, vanadium, on across, arsenic, selenium, bromine, krypton. And when you get to that noble gas krypton, and you want to go to the next one, well, you got to go back over here to rubidium because it looks like potassium. Right? So you go through the period and you have to backtrack, start over again. Those are periods. Okay? And they're numbered from top to bottom. Helium and hydrogen and helium are in the first period. Then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon are in the second period, and so forth. Okay? That's why they call it the periodic table. It is a table, and the rows designate periods. Now, the vertical columns are the groups of elements that have similar properties. So these are right here on the left. Those are the alkali metals. They all have very similar properties, and their outermost electronic structures are similar. Okay? Same thing for alkaline earths. And we skip these for temporarily. We'll come back to them later. But you have the boron group, carbon group. These have names also. The noble gases, right? That's a group. They don't react with anybody unless you really force it. Then you have the halogens, right? Y'all not too young to remember halogen light bulbs, are you? They used to put them in headlights. In fact, my car is old enough, I've got halogen headlights. Now they go LEDs, right? They used to use halogens. And they were basically a light bulb that had some iodine in it. And it created the correct spectrum of color and a bright color efficiently. And then these are the chalcogens. These are archaic names that refer to oxygen compounds. So the chalcogens are this group, and then the pnictogens are nitrogen group. Pnictogen starts with a P. I don't know why the P is silent. But those are groups, and they have similar properties. And when you get down into these transition metals, they do have some similar properties in their groups, but they're not as well defined as these groups here. Okay. For instance, the noble metals, gold, platinum, palladium, they're not in the same identical group, but they do have similar properties. And maybe we'll try to explain why that is later. Maybe not, because this course doesn't go into that depth. Right? But as far as groups go, these first two and these last six are very narrowly defined. Their groups have similar characteristics. Okay, I mentioned the triads. The concept of triads is attributed to Dobereiner, who was a German. In 1829, he came out with that theory. And then Lothar Meyer came out with actually a table in 1870, and with the concept of valency. Valency refers now, in particular, to the number of electrons in the outer shell. Those electrons are available for reactions when two elements come together. That's what they see. They see those valence electrons, and that makes the reaction happen a certain way. But they were starting to build information that would later be organized into our periodic table. Mendeleev, everybody heard of Mendeleev? Maybe you have, maybe you haven't. He was a Russian, and he noticed periods also. He was building on the work that had gone before, and The reason Mendeleev is given credit for the modern periodic table is that he used the table to make predictions. He put elements in groups and then their periods based on atomic mass. And you notice that occasionally he would come to a place where there should be an element, say in here somewhere, that had similar properties to the ones above it. But there was nothing that they knew of at that time that would fit that place at the mass that it should have been. So he left it blank. And he said, one of these days, someone's going to discover an element that fits that space, and it's going to weigh this much, and it's going to have these properties. Sure enough, they did. So his use of the periodic table to predict unknown elements was what gives him credit for the periodic table. Okay, so then where did the atomic numbers come from? Because at this time, they only knew masses, right, for this time period. They only knew masses. This was in the 19th century. And they knew masses of elements, but they didn't know what distinguished one element from another other than its properties. Along came Henry Moseley. He was a very young man. He did some groundbreaking research on X-ray spectroscopy. So what they would do would take a pure element, fire X-rays at it, and then it would re-radiate energy in certain bands of colors. Some you could see, some you couldn't. But they used spectrographs to split them apart, and each one of these elements had a unique X-ray spectrum. And if you picked one of the lines of that spectrum and your instrument was properly calibrated, you could determine what the wavelength was. And that wavelength was unique for the element. What Moseley realized was that the wavelength variation from one element to the next varied by whole number multiples. And he called those whole number multiples atomic numbers. Now he didn't attribute the atomic number at that time to the number of protons. That came later. But this is where the atomic number originated. It was fantastic work that he did, unfortunately. See the time, 1913. Pretty soon, Europe was at war. He went off to war and got killed. He was 24 years old. So that ended a brilliant career. But he did manage to give us this. Okay, so we have our periodic table organized horizontal rows and periods, vertical columns in groups. We used to call them families. I think preferred term now is groups. And I gave you these as identifiers for certain of the groups have names, right? And let's see, you got a periodic table, I think, for extra credit that you can fill out. Okay. You'll notice that in one of those items, the request is for that you identify the groups by their IUPAC number. IUPAC stands for International Union of Pure and Applied Chemists. Okay, they're the governing body, the clearinghouse for standardized information about anything having to do with chemistry. So they have decided within the past couple of decades, I guess, that these groups should be numbered just from left to right, 1, 2, 3 on across, all the way to 18. Okay, that's the new numbering system, and that's the one I want on your table. But this slide was made before then, and it uses a different grouping system. It uses the A and B system. And in some respects, this is more useful because your periodic table, if you go A's only, then you go 1A, 2A, then you skip over here to 3, 4, 5, 6, 7, and 8, or 0. what that tells you, at least for these elements up here, is a very good predictor of how many electrons you have in the valence shell. Right? So if it's A1A, that's 1 electron in the outer shell, 2 electrons, 3, 4, 5, 6, 7, 8 means a full shell. If you had any biology, sometimes they do a little chemistry spiel in biology, and they talk about the Octet Rule. If you can get 8 electrons in the outermost shell, you have a full shell and it doesn't react. Or if you have 2 elements with a deficiency, less than an octet in their outer shell, then they react to complete the octet. Right? This one might complete the octet by losing an electron. This one might complete by gaining an electron, which is what happens with sodium and chlorine. So that's why this A scheme is useful sometimes. Then, of course, when you get into the transition metals, we change it to B. But I hope I can explain why we can't include these in this octet arrangement. Oh, okay, so here's our periodic table. I should have talked about it here. Okay, how is the periodic table arranged other than periods and groups? There's one major division right here, and that's requested in your extra credit, right? The division between nonmetals and metals, right? All these are metals also. So most of the periodic table is metals, only a few nonmetals. And they have characteristics, right? Generally metals, if they're in bulk and you can polish them down, they will have a luster. They're usually very good conductors of electricity and heat, whereas the nonmetals are not. They're often malleable. If they're pure, you can bend them. You could even, pure iron, right? We think of iron in terms of steel, but pure iron is very soft. You can scratch it with your fingernail. Malleable, ductile, which is kind of a kissing cousin to malleable. Ductile just means you can stretch it. So you can stick it to a die and pull it out the other side and make it thinner and just go through die after die until you take a rod that big and it's down to like the size of a hair, only it's 100 miles long. Okay. So metals versus nonmetals. Okay. So from left to right, the atomic number increases, and from top to bottom, the atomic number increases. So all you have to do is go hydrogen like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It just works its way on down. You only have one kink when you get down to right here. The lanthanides fit right in here. That's this group. They shove them right in this crack. And then the actinides, they get shoved right in this crack. The only reason that they're pulled out like that is to keep the table compact. If you put them where they were supposed to be, you know, the table will stretch halfway across that wall. So we just put them down there. And there's value to doing it this way also, and I hope I can explain that to you later. But the position of the elements in the table is an indicator of the electronic structure of that atom. Okay, so I hope that will become clear as we move along. We'll see if we can. These are characteristics of metal. I mentioned them already. Nonmetals, instead of being malleable, they're usually brittle. They just, if you think of a metal, then what's a metal? Non-metal's the opposite. It's the easiest way to think of them. And these are a collection of characteristics. You know, a diamond is a good insulator. Oh, a heat insulator. Well, except for carbon in the form of diamond. The the reason that carbon is a good heat conductor is because of the structure. The atoms are linked together. In fact, a perfect diamond that has no flaws is a single network of carbon atoms. I mean, you can go from carbon to carbon if you're small enough, cross from one side of the diamond to the other, and never lose your step. There are no breaks. It's just a network solid. And that's why diamond is a heat conductor. But most everything else, it's non-metal, is an insulator. In fact, they use that characteristic to determine if you've got a real diamond on your finger. So you go to the jeweler, and they've got this tool, and they'll put it right up against your diamond and see how it conducts heat. If it conducts high enough rate, then they know you got a diamond. They did that to my wife's ring one time. We had an opportunity to buy what we thought was a tanzanite, the blue, and say, okay, so the person said, send me $20 for shipping and I'll send it to you. So they did. So we had it mounted in a ring. We took it to the jewelers and showed it off, and they said, that's a lovely blue diamond you have in the hand. I said, no, it's a tanzanite. We only paid $20 for it. So he said, wait a minute, let me get my instrument. So we put the instrument on it. It's a blue diamond. So whoever sold it to us didn't know their gems. So next thing we did was we immediately called our insurance company and added a rider on our policy because it was quite valuable. Okay, so there's our division, metals, non-metals. So the difference between metals and non-metals are all of these. Conductivity, electricity. Metals are generally solids. There's only one metal that's not a solid at room temperature, mercury. It's a liquid. But most metals are solids. Non-metals can exist in any form. They can be gases, solids, liquids. In fact, bromine is your liquid, right? While iodine is a solid. Chlorine's a gas. All these guys right here are gases, plus that one. Hydrogen, we have to set hydrogen off by itself because it doesn't fit anywhere well, And even though hydrogen is over here, it's not an alkali metal. Hydrogen is just hydrogen. It's just one proton, one electron, and maybe one proton and a neutron. It's a deuterium or tritium, one proton and two neutrons. But it just doesn't fit anywhere. So we just stick it over there for balance. Okay, electron shells. Now we're going to talk about where are the electrons located around the nucleus. And we can't go into the theory very deeply because we just don't have time to do all of that in one semester. But the electron shell in your book, and I added this in, is based on the principal quantum number. So there are 4 quantum numbers. That define electrons in the structure of an atom. Okay, the first one is the principal quantum number, and this one is equal to the period. Right. So the principal quantum number for lithium will be 2, and that's called the electron shell in your textbook. Right. The principal quantum number is defines the energy level. Okay. So the energy level for all of these elements, for that particular quantum number, that shell, are at the same energy level. Now there are slight differences that occur, but the overall, everything fits in this energy level somewhere. That's why we say they have approximately the same energy. That's our escape clause. And they spend most of their time at approximately the same distance from the nucleus. That's the size of the shell. Okay? So those that occupy the first shell are closer to the nucleus and lower in energy than those in the second shell. So that's a concept that will help you understand the structure of an atom. If we look at it in terms of like this, we say this is the nucleus with our protons and neutrons. Then the electrons are out here. This is the shell number 1, shell number 2. The energy level of an electron around an atom is based upon its proximity to the nucleus. So the closer it is to the nucleus, the lower its energy. The further away from the nucleus, the higher the energy. So when you think about, if you have an electron here and you add energy to it, like you shine an ultraviolet light on it, it absorbs that light. Right? If you shine energy on it, then it may have enough energy to jump to the next level. Right? So you've added energy, now it's at a higher energy level. Okay? That's the concept. The farther away from the nucleus, the higher the energy. And eventually, if you add enough energy, you can eject an electron completely from the atom. So that's the basis of the photoelectric effect. So if you have your little forgot my terms now. Your photoelectric cell. When light comes in and strikes it, it's got enough energy, it'll kick an electron off of the surface of the silicon wafer, and then the electronics picks that up as a current. So you have those electrons available to do work because you've added energy to them. Okay, now the subshells, right, we have N is the primary or the principal quantum number. Then you have L's, and each one of these principal quantums has within it sublevels called L. So they're not independent, they're dependent upon one another. This is the major category, these are subcategories of that one. Okay? So these subshells we give letters. S, P, D, F are the only ones that we're concerned with. And each one of these subshells has a maximum number of electrons that it can hold. So now we're learning how the electrons are arranged around an atom so that we can start building atoms. So this one holds 2, this one holds 6, this one can hold up to 10, this one can hold up to 14. Right? Then there's the electron orbital. And while this is the related to the energy, this is related to the shape of the space that's occupied by the electron. And this one, M sub L, the electron orbital, or the magnetic quantum number, is defines the orientation in space. For example, the p orbitals are shaped like dumbbells. Right? You can have them in this plane, or you can have them going back into the board, which will represent like this. Oops. Like that. Or you can have them, instead of this way, and this way. Right? So those are 3 dimensions. That way, this one. So the M sub L will determine which one we're talking about, right? So we could have three possible orientations for p orbitals, but which direction are they pointed, right? Is it X, Y, or Z? And that's where this one comes in. Okay. Now, each one of these electron orbitals can hold 2 electrons. And they can only hold 2 electrons if their spins are opposite. So that's the last quantum number, these 4. This one is the spin quantum number. It can either be +1/2 or -1/2. So each one of these orbitals can hold 2 electrons of opposite spin. And that's how you build your atom. We're going to focus on these 2 right here. This just explains why you have 6 here, because right now, 1, 2, 3 orientations, and each can have 2, so 2 times 3 is 6. Okay. D orbitals, you can have 5 different orientations in space, and each can have 2, so that's 10. And S can have 7 different orientations, and that's 2 times 7 is 14. So that explains where these numbers come from. But it's not essential that you understand all this stuff. If you want to do that, we have to put you in general chemistry. And then it take 2 semesters to get through it all. Okay, so how many possible orbitals can you have in this subshell of S? You can only have 1. P's, you can have 3. I mentioned that earlier. D's can have 5. S can have 7 possible orbitals. And these are examples. The S orbitals are always spherical. Those are the easiest ones. They can only have 1 orientation, sphere. The dumbbells are the P's. The D orbitals are complex dumbbells, and some have donuts. So, and all of this is calculated based on quantum theory. Right? These are not observed. You can't see them. Right? What we're doing is we're using a theory to mathematically predict where electrons should spend most of their time. It's all probability, right? So, yeah.
I was going to say, over with the orbitals, I think you see that a lot. I've seen it in cartoons before.
Maybe that's where they got it. Yeah. It's kind of like my first introduction to classical music was through cartoons, right? Or TV shows, like the William Tell Overture. That was, oh shoot, what was his name? Lone Ranger, right? The William Tell Overture. Anyway, so we have I told you about the spin. So 2 electrons can occupy the same orbital, but they have to be opposite spins. So the space in which electrons move rapidly about a nucleus is divided into shells, subshells, and orbitals. Okay. So the shell is like that principal number, N. Subshell is the L's, S, P, D, F. And the orbitals are the subcomponents of the SPDFs. Now, how do we fill up subshells? Think of an atom as you go. You got your nucleus, and the number of protons really is the only thing you're concerned with when you're building an atom. Number of neutrons, you could care less at this point. So the number of protons determines how many electrons you can have out here. So as you add protons, you increase the atomic number. You've got to add electrons to balance it. So you're basically adding electrons out here. Where do they go? Well, they go from low energy to high energy. So you start filling as you add protons, and you add protons to go 1, 2, 3, 4. And as you keep adding protons, you add electrons in higher and higher energy positions. And you do it using the Aufbau Principle. That's a German word that just means this is how you do it. Okay. And I'll show you how that's done. There's a real neat trick how to build and get most of them. Well, actually, all the ones that we're going to be interested in, you can get them right on. So this is the principle of how you fill orbitals with increasing numbers of electrons in increasing energy levels. Then we have sort of some rules that you have to obey. Hund's rule just says that when you're in a subshell, like you're in and then L's, the S, P, D's, and F's, they have sublevels. This has got one sublevel, this has got 3, this one's got 5, this one's got 7. Okay? What Hund's rule says is when you start adding electrons in here, you've got to add 1 for each one of these right here before you can go back and start pairing them up. Right? So if you have 4 electrons, say you have 2 here, 1, 2, and the reason I draw them like that and like that is for spin. Spin up, spin down. Right? And then you go in here and you got more. You have to put them spin up until you fill all those, and then you can go back and pair them up. So if they need another one, then you can do that. That's Hund's rule. You can't pair them up until you put at least 1 in each of the sublevels. And then the Pauli exclusion principle says that you can't put 2 electrons in the same orbital unless they have opposite spins. That's a simplified version. Actually, there's another version, but that is the gist. So if we obey these rules, then we can build an atom with confidence. Okay, let's see, I think this is out of your, this illustrates as we add electrons, we go from the lower levels, and then we add the electrons here, higher levels, higher levels, higher levels. When you get to up into this region, and you start adding electrons in this region, then you start getting some inversions of energies, right? In this case, the 5s orbital is lower energy than the 4d, so you have to put electrons into the 5s first before you can go into the 4d. Okay, and the reason for that is that as you start building electrons in their orbitals, they begin to interact. And that interaction lowers the energy of the 5s below the 4d. Okay. So I've got a way to do that. And you don't have to memorize that. But there's a practical way. It's called the diagonal. So if we just go in, and this also introduces the shorthand for writing electronic structures. Right? So the number 1 is going to be your principal quantum number, or your energy level. And then under there, how many of these can you have? Well, for 1, you can only have S. That's it. Can't have any more. And the reason for that is you can only have the number of levels, sublevels, as the principal number, right? So you can only have an S. If you have 2, now you can have an S and a P, right? The principle says you can have 2 sublevels, S, P is the next one up. So 3, you can have S, P, and D, because you got 3. 1, 2, 3. Then you can have for 4, you can have S, P, D, and F. Okay? Now, since we're not going any higher than F, we're just going to say 5S, 5P, 5D, 5F, because we don't have any elements that require a higher level beyond F. I mean, theoretically, there are higher levels, right? But you only get into those if you modify the atom by adding energy to it and that type of thing. We're not going to do that for this. And then you can go 6S, 6p, 6d. You could go on out, but that's all we need. And then you could go 7s, 7p. Now, how do you fill? Well, you start adding electrons in here at a diagonal, right? And then you go up here, and you hit that diagonal. And you go up here and get this diagonal. Get this one. This one. This one. This one. This one. That's how you fill them. So we're going to fill 1s first, then 2s, 2p, 3s, 3p, 4s, 3d. Notice we went to 4s before we went back to 3d, then 4p, 5s. That's the order of filling. So you add electrons until you run out. And the shorthand way to write these is, as you need them, you just write 1s, 2s, 2p, 3s, 3p, and then 4s, and then 3d, and then 4p, and then 5s, and on. But you put them in that order so that you don't make a mistake and fill the wrong one first. Okay, so let's do nitrogen. We need to know about nitrogen because we breathe it every day. So if we have N with 7 atomic number, that means we have 7 electrons, right? So we're going to use 1s, 2s, 2p, and more if we need it. So there's 2 here, right? And there's only 2 here because they're S's. P's can have 6. Let's see, did we go too far? 2, 3, 4. Yeah, we went too far. Right. So let's say 4 from 7 is 3. So we only need 3. Yeah. That's the electronic structure for nitrogen. We're done. Okay, so that's what it looks like. Your authors like to use boxes. I think that's too much drawing. I like to just use lines, right? So for this one, we'd have one line, right, for one box. We have another line for that box, and then we have 3 here, right? So these would be Hund's rule, 1, 2, 1, 2, 1, 2, 3, like that. So this would be a detailed electronic structure. It actually shows you which suborbital the electrons are in. Okay, let's try. See, I'm going to have to erase this to make room. But for our purposes, we've got our order right up here. How about sulfur? So we have sulfur. Let's see, how many electrons does it have? Let's see. 16, right? 16. Okay. So we're going to need this one, this one, this one. That gives us 10, right? So we've got 6 more. 3. We got 4 more. Right? So that was 4. So 2, 4, 10, 16. Okay? Now, this one's full, right? So we don't need to write that. But this one is not full. So it would look like 1, 2, 3, 4, like that. Okay? Barium. Barium is a big one. Where's barium? It's right down here, 56. That's a lot of electrons to put in there. We're going to do it the hard way first. 56. Okay, so we got 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. Let's see if we need all of them. Okay, 2, 4, 10, 12, 18, 20. How many in these? 10, 30, 36. Is that right? We're going to need more. 36, 38. So where do we go from here? 5s, 4. Let's see. 4s, 4p, 4d. 5p, I think. 10, 6, and then 6s. Let's see if that gets it. 2, 4, 10, 18, 20, 30, 40, 8, 56. Okay, I did something wrong. Six. So here's 5p, 4d, 5s, 4d, 5p, 6s. That's right. I think I counted wrong. So let's see. That's 10. This is 10. Let's see. 8. That's another 10. That's 10. That's 10. This is 8. This is 8. So let's see, 10, 20, 30, 40, 56. That's right, 56. Okay? So that was a mess. So there's a simpler way, right? Let's see. There's the full, complete structure. When you recognize that the barium actually has a core that's equivalent to xenon, right? If you write xenon, you got everything out to here. Xenon's exactly that same. So that would be xenon 54 would be the core, and then 6s2 would give you the rest for barium. Okay, how do I know that? All right, the periodic table is structured so that your outer shells, you have a core, they're complete once you get to a noble gas. So anything beyond that is valence. It's available for reaction. But how do I know, if I don't go through all that rigmarole, that this is 6s? Okay? The trick is to recognize what shells are being filled in what position. Right? These two are filling the s orbitals. So that's 5s, 6s. Anything over here, you're filling the p orbitals. Right? 4p, 5p, 6p, 3p, 2p. P orbitals are this group. The transition metals, you're filling d orbitals. Only with these, when it says 4, you back down to 3. So 3 Ds are filled here. This may be 4s, but these are 3 Ds. So you can see, if you run through it like that, you can see that diagonal coming through. Go ahead, yes. That's overkill at this point. So, what does that tell us? To use the abbreviated version, you just say, we're at barium, so let's back up. So back up 1, back up 2. Right? So these 6 S2 is valence, and the xenon 54 is our core. And that makes it a whole lot simpler. Okay, how we doing? Sure I'm not falling behind. Yeah, we're coming to that. Actually, I haven't jumped ahead of myself. That's okay. Stream of consciousness. The electron configuration of sodium is what? Well, if we use that filling technique, let's say sodium is 11, right? So sodium is being built based on neon, which is 10. And then that means we've only got 1 electron left over in 3s orbital. Well, okay, so they want the whole thing. So what is neon? Well, neon's going to be 1s2, and then 2s2, 2p6, which is 10, and then 3s1 or so. Okay, here's that. This is the core, right? That's the core. This is the valence. That's the electron, the only electron that's available for a reaction. Right? If we went to the right one more, we'd have 2 electrons. And magnesium has 2 electrons available in the valence. So that's why we say this first column, the alkaline metals, when they become charged, they're only charged to the extent of 1 positive, because you lose that electron, that makes it look like neon. It completes the outer shell by losing it. It's easier to lose 1 than to add 7. Okay, so that's why all of these are positive 1, and you lose 2 s's here, and you get a positive 2 charge. Then over here, you lose 2 s's and 1 of the p's, and you get a 3+ charge. But then when you go past that, your best bet is to add electrons. So in order for chlorine to look like argon, we need to add 1 electron. We add it in the p orbital. Or for sulfur, add 2, and we get argon. We don't actually get argon, we get the electronic configuration of argon, right? You still have sulfur, but its electronic structure is similar to argon. And that's one of the driving forces for reaction. Elements trying to attain that full outer shell. Okay. So each one of those groups, that's why each of the groups has similar chemical properties. Because anyone in this group is trying to lose an electron to look like a noble gas. So if it's rubidium, lose an electron, it looks like krypton. Or with cesium, lose an electron, it looks like xenon. Okay. That's what they're trying. They're tending toward the noble gas configuration. Okay, those are known as valence electrons, the ones that are easiest to lose or gain, the ones that are involved in reaction in order to give you that noble gas configuration. Right, and here's a layout of the periodic table. This is the S area, this is the P area, this is the D area. Now, helium and hydrogen are unique. Helium is not going to be a p area. Helium is going to be only an s area because it's in the first period, so it only has access to the s orbital, which is 2 electrons. Right? So that's why if you hear a non-chemist talking about it, they'll say, we're completing the octet, except for hydrogen and helium, it's a duet. The duet, everything else is octet. So this is just a reminder, as we fill electrons in these shells, we fill them lowest to highest, increasing energy. So first in gets lower energy than the next one. And that's why in a period, these, you go from left to right, as you add electrons, you get a different chemical reactivity. Okay. So the reason that these groups have elements that behave similarly is because they have the same number of valence electrons in their outer shells. Okay, so this is just a review. We divide them, the system divides them into metals and nonmetals. And then the electronic configurations help us to describe either noble gases, transition elements, these right here, noble gases, or representative elements. Okay, representative is a term that's used to describe these two groups and these. Right? So we're talking about representative elements are s orbital, p orbital filling. These are transition elements. These are noble gases. And then there's another one called inner transition. The inner transitions are these right here. Because they're in the transition group, but they're kind of inside right here. Go figure. And there's the layout. And all this stuff comes out of your textbook. Right? Elements in group 1 and 2 are referred to as S areas. Let's see if we can do some detective work here. We got time? Yeah, we got time. Consider 2 elements. One is a gas and the other is a solid. Okay, so we got a gas here and we got a solid here. We know that much. Each contains identical number of electrons in their outer shells. So the electrons are equal. And actually, we're saying in the outer shell, so the valence electrons are equal. But they're still 2 different elements, right? So we have an X and a Y. Actually, Y is not a good choice, but let's see, do we have a Z up there? No, we don't have a Z. We do have a Y, so I better not use that one. So we have 2 elements, X and Z. Each contain an identical number of electrons in their outer shell. These elements are this, and they contain this neutrons respectively. Okay. So if they're gas and solid, and they have the same number of valence electrons, then they could be from the same group, right? Same group. But if they're gas and solid, they're probably not metals. Because remember, all but one of the metals are solids. Every one of them. Right? So we need to look in the non-metal side. So if we go from have a gas and a solid together, what's a good choice? Well, we know that these are gases. That's a liquid. There's a solid. So these would have the same number of valence electrons, each group. And there's a gas, there's a solid, there's a gas, there's a solid. So these are possibilities. There's a gas and the solid in its group. Right? So let's see if we have any that look familiar. Fluorine and iodine. Fluorine's a gas, iodine's a solid. Okay, that works. Nitrogen and sulfur. Right? Nitrogen and sulfur, they're not in the same group, so B's out. Oxygen and sulfur. Okay, that's a possibility. Oxygen's a gas, sulfur's a solid. Fluorine and iodine, again. Okay, so we threw this one out. And now we need to look at contain blank and blank neutrons. Right, so let's see. If we click fluorine and iodine, so fluorine's going to be 9 here and 53 here. And then the most common isotope of fluorine would be 19, and iodine would be 127. So 19, 127. So 9 from 19 is 10, right? So 10's right for the number of neutrons, but 19 is not right, right, for fluorine. So we can throw this one out, we can throw this one out. It's either this one or this one. So how about the number of neutrons here? 74. 74 would be 127. That's true. Right. So that's a right answer. 74 neutrons. Sulfur. Well, we don't have any other choice. We got the right answer, so we don't have to look any further, do we? So it's that one. Oops. What happened? That must have been the last slide. Nope, not the last slide. There we go. I just hit the wrong button. Okay. Oh, last possibility. Okay. You're asked to determine the composition of a gas. There are 3 components with 3 different applications. They all have the same atomic number, but the number of neutrons is 0, 1, and 2. Oh, okay. They have the same atomic number. Right? This one, this one, this one. Well, actually, we don't know that. The Z's are the same. Okay. We're using them for 3 different purposes. Okay. They all have the same atomic number, so the Z's are equal. The number of neutrons is 0, 1, and 2. So neutrons here would be Z plus 1, no, Z plus 0, Z plus 1, and Z plus 2. Okay. One of the components is used as a radioactive tracer. Identify the gas. How are the 3 components referred? What are the names of each component? Okay, here's the trick. Number of neutrons. Right. What's the only element on the table that has no neutrons? In any of its isotopes? Hydrogen. Hydrogen, that's the key. Hydrogen is the only one that has an isotope with no neutrons. So that means one of them is going to be 1 here, and 1 plus 0 is 1. And then the next one has a neutron, and the next one has 2 neutrons. So there are your 3 isotopes of hydrogen. So that means hydrogen One of them, identify the gas. Okay, hydrogen is one of these. How are the three components referred? They're isotopes because they have different neutrons. Protium, deuterium, tritium. Okay. All right, that's it for chapter 3. Any questions? We'll have a review next week. And what you need to do is come back to me with, let's see, the extra credit's not due until the exam, so you keep working on that. And the, let's see, what was I holding with this? Homework, yeah. So come back to me with any problems you have after working the homework problems, and we'll iron all that stuff out. And then you can, then all you have to do is review for the next week. You do need to know your symbols, right? How to build an atom. That's important.
That's what we did today.
That's what we did today. Yeah, we were building atoms. And if you correlate that building atoms process with the periodic table, it really helps. Right? So periodic table, that's your best friend. The way it's organized now, it's just, you know which period you're in, which means you know the S's are being filled here, the P's are filled here. And then when you get down here, the D's are filled, but you have to back up one, so 4 S and then 3 D's. Right? So you can move right across there. And you may not even have to use that diagonal. Let me see what I've given you. I always have useful information at the back of the exam. So all I have on this exam is periodic table. So you don't have to string to see it. Okay. Any questions? No. Okay, so it's going to be a small group today. We're going to go in the lab in a few minutes. Let's see how we're doing on time. 10:41. Oh, we're good. Yeah, we should be able to knock this lab out and get out here early today. So let me stop the recording.